China is building floating giants nearly 1,300 feet long that can carry more than 24,000 containers in a single voyage. These ships are longer than some of America's largest aircraft carriers, powered by engines producing tens of thousands of horsepower and assembled from steel sections so massive that enormous shipyard cranes are needed just to move them. But here's what should really get your attention. Building one monster like this is not China's biggest achievement. Building them at industrial scale is. In this video, you'll see exactly how Chinese shipyards turn mountains of steel into these ocean-going giants and the massive industrial system making it possible. To understand what China is actually building, you first have to understand what 24,000 containers looks like in the real world. Shipping capacity is measured in TEUs, or 20-foot equivalent units, meaning 1 TEU represents a standard container roughly 20 feet long. Now picture one of those boxes sitting in front of you. Then imagine hundreds of them, thousands of them, until more than 24,000 TEUs are stacked across a ship, stretching nearly 1,300 feet from bow to stern. That is roughly the length of 4 American football fields placed end to end. Stand on the dock beside one, and you don't see something that feels like a conventional ship. You see a moving wall of steel rising above you, loaded with the products, machinery, electronics, and manufactured goods that keep global trade moving. And this scale creates an enormous engineering problem. Every container adds weight, while waves continuously push different sections of the hull upward and downward. A ship this long cannot simply be huge. It has to survive being bent, twisted, and stressed across thousands of miles of open ocean. That challenge begins deep inside its steel skeleton. Deep beneath those towering stacks of containers is the structure that keeps the entire giant alive. A massive steel skeleton engineered to survive forces that never stop changing. A mega container ship may look rigid from the dock, but at sea, its hull is constantly responding to waves. When the bow and stern are lifted while the center loses support, the ship experiences one kind of bending stress. When the middle rises on a wave while both ends drop, the forces reverse. Add tens of thousands of loaded containers, and the structure must withstand enormous bending and twisting without losing its integrity. Chinese shipyards solve this with high-strength steel structures built around the keel, reinforced hull sections, bulkheads, decks, double-bottom structures, and enormous cargo holds fitted with cell guides that keep containers aligned. If you could stand inside an empty hold, you would feel less like you were inside a ship and more like you were standing at the bottom of a steel building. But designing this skeleton creates another problem. A nearly 1,300-foot vessel is simply too enormous to manufacture as one continuous structure. So China doesn't build the ship in one piece. So China doesn't build a 1,300-foot container ship as one ship. It builds a collection of enormous steel structures and turns them into one. Inside a modern Chinese shipyard, thick steel plates are cut into precise shapes, bent into curved hull sections, reinforced with beams, and welded into panels. Those panels become subassemblies. The subassemblies become blocks. And eventually those blocks grow into sections so large that a worker standing beside one can look almost insignificant. This modular construction method solves a basic problem of scale. Instead of forcing thousands of workers to build everything in one location, different sections can be fabricated and outfitted across multiple production areas at the same time. Pipes, electrical systems, structural supports, and other equipment can be installed before many blocks ever reach the dry dock. Then comes one of the most visually astonishing stages of the entire process. Massive transporters carry these sections through the shipyard, while giant gantry cranes lift blocks weighing hundreds or even thousands of tons and position them over the growing hull. Imagine standing underneath one of those cranes as a piece of ship the size of a building moves slowly through the air above you. At this scale, a mistake measured in inches can become a major engineering problem. Each block has to align with the surrounding structure before crews can weld the sections together, inspect the joints, and continue assembling the hull. Piece by piece, what looked like disconnected mountains of steel begins to form a bow cargo holds, engine spaces, and eventually the unmistakable shape of a mega container ship. But there is a point when simply adding more steel is no longer enough. Before key sections of this floating giant are closed around its machinery spaces, engineers must deal with something just as extraordinary as the hull itself. The enormous engine that will eventually push hundreds of thousands of tons across the ocean. To move a ship this massive, China needs an engine that looks less like a machine and more like part of a building. Deep inside the stern of a mega container ship sits a huge, low-speed marine diesel engine, built around cylinders, pistons, connecting rods, and a crankshaft operating on a scale most people never encounter. Stand beside one of these components, and you immediately understand the problem. The engine is not designed to make the ship accelerate quickly. It is designed to generate enormous torque efficiently, hour after hour, while pushing a vessel loaded with thousands of containers across entire oceans. Depending on the specific ship and engine configuration, power output can reach tens of thousands of horsepower, driving an enormous propeller through a direct shaft system. And that slow rotation is exactly the point. Rather than spinning at the extreme speeds you associate with a car or jet engine, these marine engines can turn relatively slowly while producing tremendous force at the propeller. I think this is where the scale becomes easiest to appreciate. You are looking at machinery whose individual components can be large enough to stand beside, yet every movement must remain precisely controlled for voyages stretching thousands of miles. Lubrication, cooling, fuel injection, exhaust treatment, and monitoring systems all have to work continuously because an engine failure far from port is not a minor inconvenience. It can immobilize one of the largest moving structures on Earth, but producing enough force to move this steel giant is only half the engineering battle. Out on open water, traveling forward is relatively straightforward. Bring that same nearly 1,300-foot vessel toward a crowded terminal, however, and an entirely different problem appears. How do you precisely maneuver something longer than 4 football fields when there is almost no room for error? Moving a nearly 1,300-foot ship is one thing. Controlling it inside a crowded port is another. From the navigation bridge, the bow can sit hundreds of feet ahead, while towering stacks of containers restrict what the crew can see around them. The ship relies on its massive rudder and propeller at sea, but at low speeds, maneuverability becomes far more difficult. That is where bow thrusters, tugboats, radar, electronic navigation systems, and constant communication with pilots and port control become critical. You might be looking at one of the largest moving machines ever constructed, yet relatively few people on the bridge are responsible for guiding it toward a berth with extraordinary precision. Thousands of tons of steel cannot stop or turn instantly just because someone moves a control. Every maneuver must anticipate how this enormous mass will respond seconds or even minutes later. And those people don't simply operate this floating giant. For weeks at a time, they actually live inside it. Hidden among the containers is essentially a small building where the crew works, eats, sleeps, and lives for weeks at sea. Inside the accommodation structure are cabins, a galley, dining areas, storage spaces, recreation rooms, medical facilities, and emergency control systems, with the navigation bridge positioned above them. Imagine finishing a shift surrounded by thousands of containers, then walking downstairs to eat dinner or sleep while an enormous engine continues turning beneath you. It is a remarkable contrast. A floating city of cargo operated by a surprisingly small human community. But keeping that city moving across thousands of ocean miles creates another challenge: fuel. For a ship, this enormous fuel is not just an operating expense, it is one of the central engineering problems. Every additional ton of steel and cargo must be pushed through water for thousands of miles, and water creates relentless resistance against the hull. That is why Chinese shipbuilders and marine engineers focus heavily on hydrodynamic optimization, shaping the hull, bow, stern, and propulsion system so the vessel can move more efficiently without simply demanding more power. Propeller design, engine efficiency, route planning, and operating speed all matter because even a small improvement can become significant across repeated long-distance voyages. This is also why bigger ships can make economic sense. If one vessel carries more containers while keeping fuel consumption per container under control, shipping lines can potentially move each box at a lower cost. But size creates its own penalty. The bigger the ship becomes, the more carefully every source of wasted energy has to be controlled. And the pressure to reduce emissions is pushing Chinese shipyards toward vessels designed for LNG, methanol, and other alternative fuel systems alongside conventional marine fuels. That creates another engineering challenge most passengers will never see. A different fuel may require completely different tanks, piping, safety systems, and machinery. With LNG, the problem becomes extreme. How do you safely store enormous quantities of fuel at roughly 260 degrees below zero Fahrenheit inside a ship carrying thousands of containers? Storing LNG inside a mega container ship means keeping fuel at roughly minus 260 degrees Fahrenheit, cold enough to remain liquid and compact enough for long-distance voyages. That requires heavily insulated cryogenic tanks, specialized piping, monitoring equipment, ventilation, and safety systems designed to keep the fuel isolated from the rest of the vessel. On LNG-capable ships built in China, engineers must integrate this infrastructure without sacrificing more cargo space than necessary because every section occupied by fuel is space that cannot carry containers. The fuel then feeds a dual-fuel propulsion system capable of operating under different conditions. If you could cut the ship open, you would see containers above, enormous tanks and machinery within the hull, and the engine driving the propeller behind them. What looks simple from the shoreline is actually thousands of interconnected systems working as one machine. And before China can deliver that machine, engineers have to prove that every critical system actually works at sea. After months of fabrication, welding, installation, and inspection, the moment finally comes when the steel giant meets the water. The dry dock is flooded, tugboats guide the vessel out, and outfitting and testing prepare it for the most important examination of all: sea trials. Engineers test propulsion, steering, navigation, emergency systems, machinery performance, vibration, and the ship's behavior under real operating conditions. You can design every component on a computer and inspect thousands of welds on land, but the ocean delivers the final verdict. A nearly 1,300-foot machine must prove that millions of components can function together as one reliable vessel. Once those trials and required inspections are completed, the ship can finally be delivered and sent into commercial service. But watch what happens when it leaves the shipyard. Behind it, steel is already being cut, blocks assembled, and another enormous hull is taking shape. Because one giant ship was never the real story. One 24,000 TEU container ship is an extraordinary engineering achievement. But China's real advantage becomes visible when you stop looking at one ship and start looking across the shipyard. Behind a newly completed vessel, other hulls can already be taking shape. Steel plates are being cut, blocks welded, engines prepared, and giant cranes are moving sections for ships at different stages of construction. Zoom out farther, and the picture becomes even larger. Major Chinese builders operate enormous facilities supported by dense networks of steel producers, equipment manufacturers, marine engine suppliers, logistics companies, ports, and specialized workers. This is what transforms shipbuilding from a single engineering project into an industrial production system. A mega container ship requires an astonishing number of components and processes to arrive in the correct sequence. If critical equipment is delayed, construction schedules can be disrupted. If blocks do not align, later stages suffer. Scale only works when the entire chain works with it. And that is why the most impressive sight is not necessarily a finished 1,300-foot vessel leaving the dock. It is another one already forming behind it. To understand why global shipping companies continue placing major orders with Chinese yards, you have to look beyond the ships and into the industrial ecosystem producing them. Global shipping companies do not order billion-dollar fleets from China simply because Chinese shipyards can build something big. They come because an enormous industrial network exists behind those yards. Building a mega container ship requires far more than steel and labor. Shipyards need marine engines, propulsion systems, electrical equipment, navigation technology, pumps, valves, miles of piping and cables, coatings, cranes, and thousands of specialized components delivered in the correct sequence. China has spent decades developing manufacturing clusters capable of supporting much of that demand at enormous scale. For a ship owner, this matters because price is only part of the equation. Construction capacity, delivery schedules, technical capability, supplier access, and the ability to handle multiple large orders can determine whether an entire fleet expansion succeeds. I think this is the key distinction. China is not competing with a single shipyard. It is competing with an industrial ecosystem. Steel producers feed component manufacturers, suppliers feed shipyards, and enormous ports and logistics networks sit nearby. That concentration helps explain how Chinese yards can manage increasingly sophisticated commercial vessels at scale. But another question remains. If building these giants requires so much infrastructure and investment, why does the shipping industry keep demanding even larger ships? The answer is economics. Every additional container can potentially reduce the cost of moving each individual box across an ocean. A mega container ship concentrates enormous cargo capacity into a single voyage, allowing shipping lines to spread fuel, crew, and operating costs across thousands more containers. But bigger does not automatically mean better. A nearly 1,300-foot vessel demands deeper channels, longer berths, enormous container cranes, wider turning basins, and ports capable of processing huge cargo volumes quickly. If that infrastructure cannot keep up, the efficiency gained at sea can disappear on land. The ship becomes larger, but so does everything required to support it. That is why these vessels represent more than a competition for size. They are part of a much larger logistics system, connecting factories, ports, railways, trucks, warehouses, and consumers. And nowhere is that connection more visible than in China, where the ships being built can eventually carry manufactured goods from Chinese factories to markets thousands of miles away. This is where the scale of these ships becomes personal. A container can leave a Chinese factory carrying electronics, machinery, furniture, clothing, or appliances, travel by truck or rail to a massive port, and then be lifted onto one of these ocean-going giants. Weeks later, that same box may arrive thousands of miles away before continuing toward a warehouse, store, or even something you eventually buy. The ship is therefore more than steel and horsepower. It is a moving link between China's manufacturing system and global consumers. And once you see that connection, the biggest machine in this story suddenly isn't the ship at all. The real machine is the industrial system behind the ship. Steel mills produce the material. Factories manufacture thousands of components. Engineers turn designs into working systems. Shipyards assemble enormous blocks. Ports connect the finished vessel to global trade, and logistics networks keep everything moving. A 1,300-foot container ship may be the most visible result, but it is only the final product of something much larger. China didn't simply learn how to build gigantic ships, it built an industrial ecosystem capable of building them again and again. Nearly 1,300 feet of steel and more than 24,000 containers may be what catches your eye. But the real story is what stands behind them. China's mega container ships reveal something much larger, an industrial system capable of turning steel, engineering, infrastructure, and human expertise into floating giants and then doing it again.